The minerals here on Earth are going to exhibit different properties based on the structure of the minerals and the crystalline structure, the compounds that make it up, so on. This video is going to go through some of the basic physical properties of minerals. One of the first properties that's most obvious is the color of a mineral. For instance, gold has this yellowish color, silver has this shiny grayish color. Unfortunately, color is not always very useful. One reason is because it can be influenced by trace impurities. For example, salt is a white color. But have you ever seen pink salt or orange salt? They're all over the earth because there are trace impurities inside of the salt. Not harmful, they're definitely fine to eat, but because there are those impurities, it just gives it a different color. A property that is more useful than color is what we call the streak. Basically, if you shave off a little bit of the mineral from the stone, then it's going to turn into a powder. The color of that powder is more consistent than the color of the stone itself. And that's because when you take the powder, you're usually filtering out some of those impurities. Now, another one that's probably very critical in identifying one mineral from another is the hardness. The hardness is defined as the resistance to scratching. We use what's called the Mohs hardness scale, which you can see here in this table. It uses 10 different tests, 10 test minerals, with increasing hardnesses. So you take a mineral and you scratch it with one of these materials in the table, and that will tell, if it scratches, that will tell you the hardness. Talc is the softest of minerals. Talc is very similar to soap. It is also what we use for chalk on chalkboards, so on. Very, very soft. So if a material can be scratched by talc, it's a very soft material indeed. Gypsum is slightly harder, calcite harder still, and so on as you go through the list. Quartz is a big one that has a hardness of 7. Diamonds are some of the hardest minerals in the world, and so that's given a hardness scale of 10. If a diamond doesn't scratch a mineral, then it is a very hard mineral indeed. Here are two good examples of hardness. On the top you have gypsum, which we saw in the table previous slide, has a hardness of 2. You can take your fingernail and scratch gypsum. That's how soft gypsum is. Whereas on the bottom structure, you have quartz, which has a hardness of 7. Now, quartz is extremely resistant. You can take a metal file to quartz and it won't scratch it because of the hardness of the quartz. What determines the hardness is the strength of the bonds and the structure of the crystalline pattern within all of these minerals. Here are some more physical properties that help distinguish one mineral from another. The crystal form. That's basically talking about the arrangement of atoms. We talked about that a little bit earlier. Salt has this cubic crystal structure, whereas ice crystals have a hexagonal shape. Just as a side note, the hexagonal pattern for ice, that is why snowflakes often have 6 points, is because of this hexagonal pattern. Cleavage is the tendency of minerals to break along smooth planes. For instance, if you go out and take any ordinary rock and you take a pick to it and break it in half, generally it's a very rough surface. Whereas if you take a big block of salt, halite, you use the same pick to cut it in half, it will generally break with a very smooth side. That is what we call cleavage. Fracture is pretty much the opposite of cleavage. It's talking about the irregularities in these broken surfaces. When we talk about luster, we talk about the surface sheen, how bright the mineral is. For instance, you take a piece of granite, often doesn't have a whole lot of shininess to it, but you have a piece of polished silver and it reflects your face. It's that shiny. And so silver has much more luster. Density is also another property that determines the physical nature of minerals. We've defined density way back at the beginning of this course as the ratio of mass to volume, or mass divided by volume. Another alternative to density is called specific gravity. That's the ratio of mineral density to that of water. We'll talk about that in the next slide. When we talk about density, we're talking about two different factors. There's the kind of atoms that make up the mineral, the density of those atoms that make up the mineral. And there's also how closely packed those atoms are to each other in the crystal lattice. A little more on specific gravity. Again, we just saw the definition. It's the ratio of mineral density to that of water. Just for reference, the density of water is 1 gram per milliliter. That's the definition of a milliliter, is the volume of 1 gram of water. In other units, that would be 1,000 kilograms per cubic meter. You could see either of these units. So let's do a quick example. Let's say that we have a crystal that has a mass of 4.08 grams. And it's the mineral augite, and it measures 1.43 centimeters long, 0.98 centimeters wide, and 0.89 centimeters high. The cleavage of mineral augite causes it to break into a rectangular solid, so we've got more of a cubic structure. Question is, what is its specific gravity? Well, remember that density is mass divided by volume. We have the mass, 4.08 grams, but we don't have the volume yet. Well, since this is a cube, volume is easy. It's length times width times height. So that's going to be 1.43 centimeters times 0.98 centimeters times 0.89 centimeters, just taking the length, width, and height from the question. Multiply all those together, and you get 1.247 cubic centimeters. Now, it's important to note that the definition of 1 cubic centimeter is the same as the definition of 1 milliliter. So this is going to be also 1.247 milliliters. So the density then is mass, 4.08 grams, divided by the volume, 1.247 milliliters, which is going to give us a density of 3.27 grams per milliliter. Now, this is good enough. I'm going to give you the kilograms per cubic meter version of this, because we're going to use it just to show why specific gravity is so useful. So that would be 3,270 kilograms per cubic meter. Okay, so the specific gravity is defined as the density of your mineral. This little P-looking shape is the symbol for density, divided by the density of water. So that is going to be 3.27 grams per milliliter divided by the density of water, which is 1.0 grams per milliliter. Well, that just becomes 3.27. There you go. That is the specific gravity of mineral augite. Now, what if you have the other unit of density, 3,270 kilograms per cubic meter. Well, guess what? You're going to find we have the same thing. So there's the density of augite, 3,270 kilograms per cubic meter, divided by the density of water, which is 1,000 kilograms per cubic meter. Well, 3,270 divided by 1,000 is, guess what? 3.27, exact same number. This is why specific gravity is so useful. Specific gravity is going to be the same independent of the units of density.